Well, hello and welcome to week 2 for EDUC1635. This week we're going to be looking at the idea of numeracy and mental computation and touching on the fluency proficiency of the Australian curriculum. I hope you enjoyed the week 1 content, and more importantly I hope you enjoyed the tutorial and you were actively engaged in that as well. So let's get let's start. Now, what do you think this word numeracy means? Perhaps just take a moment, stop the video, and have a think around what the concept of numeracy means to you, and see if you can find some words around your own definition. When you're ready, just restart the video, and we'll continue with the lecture. Now, okay, hopefully you've been able to have your own definition of what you think numeracy means. Let's have a look at what it might look like in real life. Okay, let's have a good look at this. It's a little bit hard to read with the shopping trolleys, etc. But what do you think's wrong with this picture? Well, we're obviously in a grocery store. There's some specials being advertised. Something's being advertised at half price in a very big font, and it's taking a lot of that space. And on either side, the left and right, we've got these ideas of the special. So we assume that the special is it's now $2 and it's half price. Well, let's have a little bit more closely, look a little bit more closely at that half price. Okay, so when we have a look, and sorry it's a little bit blurry, but what's not easy to see is this was $6, whatever it was they're advertising. Well, let's have a look what it is. It's quite a laugh. But whatever it was $6. It's now $2 and you're saving $4, and they're talking about it's half price. Now, if you've got my sense of humour, when you look at what the actual item is they're selling, and it's a little bit blurry, but it's a NAPLAN style workbook for Year 3 numeracy, we can only assume whoever put that price list together, or that half price costing, didn't perhaps pass their Year 3 NAPLAN. Because of course, as you would well know, if it was originally $6, half price would make it $3. Saving $4 on a $6 initial cost is definitely not half price. Numeracy, people didn't understand the general tenet of what half meant. So here we go. There's the 3 key elements. It's half price, and it's all around the NAPLAN numeracy workbook. Perhaps they needed to complete it themselves. So what is numeracy? Well, the State Department of Victoria in 2017 came up with this really nice definition. Numeracy. Children and young people need increasingly sophisticated levels of language and mathematics in order to take care of their health and well-being, personal, participate in the workforce, working life, and make a positive contribute to a democratic society, societal outcomes. Mathematics supports us to analyse and reason about the nature of the world. Notice that that's the definition of numeracy, which is an all-encompassing one, but they identify in that last paragraph that mathematics supports us to analyse and reason about the nature of the world. So what is it? Is numeracy mathematics, or is numeracy something different to mathematics? Well, let's have another little practice of being numerate. Which offer will you take? Would you like to pay $10 per month, or would you like to pay $199 for 18 months? Planet Fitness, which is the best offer for you? Well, hopefully, if your maths is a little bit beyond Year 3 numeracy, you'd understand that 18 months times $10 a month is only $180. So why would I be paying more for an 18-month contract which locks me in, when if I just paid it per month, I'm going to get it much cheaper? What are we doing here? We're not just using mathematics to understand the comparison between $10 per month. We're using our numeracy to compare what it's like between $199 for 18 months, or if we're going to pay per month, and what we pay per month over an 18-month period. A little bit similar, but you can see the understanding. We're comparing those two things. So hopefully we're being numerate. Is it such a bargain? What about this one? Here's a clearance. It was $52.99. It's now $47.99, and you saved $12. Wow, that's amazing. If you raced in and bought that thinking you were going to save $12, was it such a bargain? Well, you could probably take them to the standards authority, because in my mathematics, if it started off at $52.99 and we saved $12, well, that should surely only take it down to $40.99, not $47.99. And I think as a consumer, you could rightly so perhaps demand, if that's the right word, that you get, if you want to buy whatever it is they're advertising, you get it actually at the $12 saving. So instead of paying $47.99, you end up paying $40.99. Again, it's the simple mathematics that's there. It's a subtraction, one from t'other, and then it's a comparison of what's better. But it's the interpretation of that comparison is where we start to delve into numeracy. Let's keep going. What about driving? How complex is driving? Well, Dave Tout in the Australian Council of Education Research in 2019 developed this nice little graphic around numeracy and driving. So look at the 5 key areas of running a car, buying a car, getting your license, getting around, drink driving, the penalties for that, and having accidents. And look at the numeracy that sits around that. So, for example, running a car, fixing your own car, can you do that? Can you run to a sort of a methodology for fixing your car? Can you diagnose what's wrong with it? If you fix your own car, you're going to need to know the cost of spare parts. There's some mathematics. The numeracy would be comparing between different providers of those parts. Running a car, you're going to have to pay for servicing. Can you afford it this month? It's in your budget. Running costs. Can you afford to run a big V8, or are you better off driving an electric car? What's the fuel economy? How do we compare different economies of different cars? And of course, the petrol price is a big one, and not just being mathematically oriented, but numerate. You'd be numerate if you were to say, I'm getting my petrol at the garage typically on a Tuesday, because I know that that's when petrol prices are much cheaper. Insurances, of course, come down to dollars and cents, but registration, you're starting to make some decisions around, should I register the car for a month at this cost, or 3 months at this cost, or 6 months at this cost, or 12 months at that cost? And you might start to make some calculations. Oh, if I pay for it over 12 months, I'm going to save $3 compared to over 6 months. But can I afford that? Am I better off just paying twice every 6 months, managing my money better rather than saving $3 over 12 months? So lots of decisions around just having a car that not just involve mathematics, but also you being numerate, being able to interpret that mathematics to suit your lifestyle. So just again, take a time to pause the video when you're ready and write down at least 5 numeracy practices that you utilized when you ran a sports carnival, or you might think about running a sports carnival or participating in one. Or if you're applying for a loan, what are 5 numeracy practices that you might need? What about just getting yourself to uni? What numeracy would be involved in that simple task or complex? And perhaps you wanted to buy a new car. So again, just stop the video when you're ready, write down at least 5 practices, choose one of those topics, and when you're ready, resume the video itself. Okay, I hope you managed to do that, and we'll unpack those a little bit later as well. So really important to understand, JASB in 2021 says numeracy is not a synonym for mathematics, but the two are clearly interrelated. And the National Numeracy Review report in 2008 said the implemented mathematics curriculum has a responsibility for introducing mathematics which is able to underpin numeracy. So clearly there are these two separate terms. There's the idea of numeracy, and then there's the mathematics that underpins or contributes to that numerate understanding. I always compare it to literacy because people seem to understand that being literate, I beg your pardon, doesn't simply mean being able to read, but certainly being able to read and contributes to your being literate. Being able to spell of itself doesn't mean that you are literate, but spelling underpins your ability to be literate. Comprehension. All of those elements of reading, spelling, grammar, comprehension, etc. combine to make you a literate person. Similarly, in mathematics, there's lots of different elements of mathematics which are used or combined then for your reasoning and thinking to turn you into a numerate person. So again, let's look at JASB. Numeracy is not a synonym for mathematics, but the two are clearly interrelated. And if you're not sure about this, maybe have a bit of a conversation with your tutor and unpack a little bit further. In the West Australian Mathematics curriculum / the Australian Mathematics curriculum, this little table is quite nice because you can see in the dark at the top, it talks about the numeracy continuum, and it breaks numeracy down into these 6 areas: estimating and calculating with whole numbers, recognizing and using patterns and relationships, and I'll talk to you more about patterns and the importance of them, using fractions, decimals, percentages, ratios and rates, spatial reasoning, statistical information, and using measurement. All of those elements combine to help you be a numerate person. And if we have a look on the right-hand column under West Australian Mathematics, these are broken down into what we call 3 strands, or 3 strands under the Australian curriculum. So estimating and calculating with whole numbers come under number and algebra, but are also an element of measurement and geometry. Patterns and relationships, number and algebra, but also statistics and probability. And you can read down that list and see how those 3 strands relate to each of those things on the numeracy curriculum, continuum if you like. And if we go back to the top, estimating and calculating with whole numbers, which are under the number and algebra strand and the measurement and geometry strands, and look at the little description at the bottom of that table, and this element involves students using numbers for different purposes. Students apply skills in estimating and calculating with whole numbers to solve and model everyday problems in a wide range of authentic contexts using efficient, really important term, mental, written and digital strategies. They identify situations where money is used and apply their knowledge, etc. And that description goes on. I've just captured that first part. So one of the key things that I see in this is the beginning of the second sentences. Students apply skills in estimating. And again, we've got to get past this concept that there's only a single answer for mathematics when we have an equation, if you like. Sometimes being numerate, having that skills of being able to estimate or approximate or come close to the solution is sufficient. We don't always need, sometimes we do, but we don't always need to get to the exact final answer. So again, numeracy versus mathematics, the elements of mathematics, those things that combine to help you be a numerate person. There we go. So Simon talks about in 2021 critical numeracy. So what's critical numeracy? A critical appreciation of how mathematics is used to describe and explain the world and make discerning decisions about everyday issues that involve mathematics. So let's look at some of the key words in this definition. It's a critical appreciation. So appreciation is really important because that means we understand and can apply a value to it, I suppose. I'm trying to think we don't always have to like something in appreciation, but a critical appreciation just means that we can acknowledge that something's going on that's quite amazing, if you like. What else? Well, it's used to describe and explain the world around us, and more importantly, it helps us make discerning decisions. That's being numerate, making those discerning decisions. And if you look back at those examples from the shops where they got the discount wrong or the half price wrong, that helps us to make these discerning decisions so we don't disadvantage ourselves in terms of interacting with the mathematics of the world around us. Back in ancient times, having the power meant having access to data. Today, having power means knowing what to ignore, from Harari. So data in ancient times was an all-powerful thing, and if you were able to access that and proudly proclaim that you had that knowledge, if you like, you were held in high esteem. But today, having that power means knowing what to ignore and what to take notice of. And we come back to Simon's definition about discerning decisions. So being numerate, and in fact having critical numeracy, helps us knowing what to ignore so that we can make better decisions in our world and the mathematics that's around. Okay, let's have a look at this idea of critical numeracy. And you might remember last week I told you in the lecture, I mentioned in the lecture that the language of mathematics was quite varied, that we had words, we had numbers, We had symbols such as the addition sign, square root sign. We had and pictorial elements such as this graph. And there needs to be a numeracy around even just reading this graph. In fact, we'd probably call it a literacy, in fact, and being able to identify what this story is telling us. So we've got a pictorial, and we can see the title at the top is The Daily Temperature Showing a Stable Weather Pattern. And if we used our skills of being graphically literate, we would see that the blue line has ups and downs, the dots are joined, and we could interpret that the horizontal axis looks like, oh yes, it's labelled days of the week, it's divided into Monday, Tuesday, etc. And we can see that on Friday, the blue dot that's corresponding to Friday is the highest. And if we look across on the left-hand vertical axis, we can see that's measured in degrees Celsius. It starts at 0 with increments of 10. And we could estimate roughly, we don't need to know exactly, that on Friday the highest temperature was around about 26 degrees Celsius. And we can see the lowest, although pretty close, was on Sunday, and we could say that was about 16. Excuse my croaky voice. So we can interpret that, and we know that we use a line graph because temperature is constant. So all of those times we assume the temperature is being measured at not just on midday on Friday, but at 2 minutes to midday on the Friday and 4 minutes past midday on Friday. So we use a line graph to show that that's a continuous measurement. Again, a critical literacy to understand the numeracy of the graph. Let's have a look at this graph. Oops, sorry. Let's have a look at this graph. And okay, so it's the same graph, but wow. Let's have a look at the peaks and troughs. So when you look at that, does it tell you that temperature variation is actually quite dramatic compared to the one on the left-hand side? There's not a lot of variation between the highs and the lows. But certainly the second graph seems to be, there's a greater variation between the highs and the lows. Let's start to use our critical numeracy skills to analyse this graph itself. So it's still showing daily temperatures. It still has days of the week in the bottom. It still has degrees Celsius on the vertical axis. However, instead of starting at 0 as the left-hand graph did, this one starts at 14. Oh, okay. And no longer is the graph divided into increments of 10 degrees. They're divided into degrees. So what's the difference between these two graphs? Well, hopefully you'll be able to see fairly clearly that there's no difference. They're actually representing the same thing. The only difference is the scale of the vertical axis, the degrees C. The right-hand graph actually starts at 14 and not at 0. So again, a critical literacy, because if we looked at that and didn't really carefully study the left-hand or the vertical axis, we could assume that on Sunday, oh, that's around about 1 degree. That must be really cold, where in fact it was 15. So who would be advantaged in presenting the data as table 1, and who might present it as table 2? Well, perhaps table 2 is an air conditioning salesman to say, wow, look at the big variations in temperature that we have over the week. You're going to have to buy one of my super duper U-Butte heating and cooling air conditioners so that you can manage your life into, you know, a constant temperature in your house. Who's going to be interested in table 1 perhaps? Well, I don't know, maybe someone in the tourist industry convincing people to come to Perth and have a holiday in Perth, because have a look, our temperatures vary very little. You know, we go from a high of 16 to about, a high of 26 to about a high of 16. You know, there's not a lot of variation. The temperature's fairly even all year around. So again, we need some critical numeracy skills or critical literacy too, to be able to understand and compare and make some decisions about both of those graphs. So when we look at critical numeracy, we need to have a think about whose views being promoted and to what advantage. And certainly we don't want to have this to our own disadvantage. What arguments are being promoted, and is there any bias? Well, we could see there was certainly bias in those two graphs. Who's being empowered and who is being disempowered? And if it's a salesman to a seller to a buyer sort of relationship, then you would think that the salesman's being empowered and the buyer is being disempowered. And then what mathematics is being used, and is it being used appropriately? Is it appropriate to start a graph at 14, as in that previous slide, or should we always start at 0? But there are in fact rules that graph didn't apply to by starting at 14. But anyway, we need to be aware of those things. So have a think. Why do you think motor vehicles are advertised as 19,990 rather than 20,000? Well, when we look at that really quickly, we don't sort of do the maths so much, but we're more swayed by the fact that we're looking at 19,000s versus 20,000s, as opposed to only a $10 difference between the two. So again, whose views being promoted and what to advantage? What arguments are being promoted and is there any bias? Who's being empowered and who's being disempowered? And what's the mathematics being used and is it being used appropriately? And maybe you could use those 4 questions when you're looking at the why are motor vehicles advertised so $10 cheap basically. And here's Goss, Goose, Dole and Geiger in 2012 setting up a model for numeracy in the 21st century, and they've called this critical orientation. But if you have a look at the 3 points on the peaks of those triangles, it's comprised of, in their proposal anyway, of mathematical knowledge, disposition, my favourite word from last week, and I'll continue with my Duke group this week around that, and then the tools of mathematics. Coming to the centre of all that is all the contextual understanding. And we can see at the peaks of that context triangle, we have things such as citizenship, personal social responsibilities, and then work. And then within each of those triangles, we have these ideas of confidence, flexibility, initiative, and risk coming off contexts towards the dispositions. The tools that we need, the representational tools, the physical and digital tools, and we'll talk to you at length about the concrete representational abstract model for learning mathematics and teaching mathematics. And then, of course, there's this last part around problem solving, estimation, conceptual understanding, and the skills that are required. So quite a nice little breakdown in terms of this idea of what's involved in being a critically numerate. One of the things we really need to dispel, and one of my real concerns, is we don't suddenly think teach children that maths is magic. Maths is magic because it's beautiful, but it's not magic because there are things that happen that we don't understand. We always need to make sure that we are teaching for understanding, so the students really understand that the magic happens in their brain and it's not a sleight of hand. We're not pulling rabbits out of the hat. We're not trying to trick them in any way. We're actually giving them some solid some understanding. So while some people might think maths is magic, and if you think that maths is magic because it's beautiful, like me, great. But it's not math magic in that we're trying to trick the students into their knowledge and believe things that they can't see that aren't in front of them. We want them to be good, strong mathematical thinkers. We want them to be strongly numerate. And again, when things get really complex, pardon me, sir, could you please explain step 3? And step 3 is a leap of faith. No, we've got to make sure that we give the students a strong understanding of the steps that we build towards, from a problem towards a solution, whatever that might look like. No, it's not magic. There's reasons for that. And it's not just trust me, everything will be all right later. We must know and understand, and your job as a teacher is to be able to break down these little steps of understanding so that there's no leap of faith occurring, so the kids don't think it's magic. You can clearly explain why we're moving from one step of a process to another. And over the next 12 weeks, you'll be getting this knowledge, and over the remainder of your course as well. So let's move on to mental computation. In some cases, students will use informal jottings on paper to help keep track of their thinking, and it shouldn't be discouraged. I mean, think about your own self in your own life when you're faced with a problem that involves some sort of mathematical thinking, mathematical understanding. How often do you take out your phone or jot it down, or a piece of paper? Just scribble down some notes so that you can keep track of things. So we always tend to start with this idea of mental computation because we can build up some really strong understandings, some mathematical conceptual development through mental, and we can start to develop that idea of a strongly numerate person because they're understanding the mathematics involved, they're not just adhering to it. So choice is not between fully mental approaches and standard written approaches. There's a blend that sits there. But to be more accurate and flexible with mental computation, again, there's that word flexibility. Now, we might have spent our time chanting tables and hating it because it was so inflexible. But now the process is we need to build this methodology and this understanding really flexibly. So to be able to do that, we need to understand numbers. We need to understand operations, addition, subtraction, multiplication, division, etc. We need to know our number facts, such as 2 + 2 = 4 or 3 × 6 is 18. We need to know those to help us not to take up the memory to be able to create some more complex mathematical processes or understanding. And we also need to estimate. We need to know whether our answer that we're getting is around about what we think it should be. And again, that builds in those skills of, of numeracy. And if we have a look at the thinker, here we go, 5 + 6 + 2 is 13. 13 takes 7 is 6, and that'll equal Saturday. Well, if we were to be able to look at how that works, it's a little bit a math of magic to me. Maybe we can talk about that a little bit more in the tutorial when it comes up. So, Northcote and Macintosh, Alistair Macintosh out of WA, a long time ago, but the research that they did said that most adults, up to 89% of adults, do not use standard written algorithms in daily life. And they mostly use strategies, or you can appreciate back in 1999, if you were born then, that a calculator was used for problems that people couldn't do mentally. Mathematics or adults had a lot of trouble shifting on from purely mental strategies actually to be able to accept the use of a calculator to help compute in those cases. And now we hardly even see a calculator other than if it's on our phone. We've got other processes to do that. But the most important thing is, if most adults don't use standard written algorithms, we don't need to focus most of our time getting kids to learn these standard written algorithms in a rote fashion. It's just not what they would do in real life, and there's a disconnect. Or, like the children, as I said in the slide before, we just use a combination of jottings. We just write things down, and it doesn't have a structure or a formula, and it sits all over the page, but it makes sense to us. And that's us being numerate in using the mathematics that we use to make sense. Again, the comparison between Northcott and Macintosh in 1999 and Northcott and Linda Marshall in 2016. About the same percentage of people in both times used mental computation most of the time, at least 85% of the time. About the same number, about 10, used written computations. Interestingly enough, a greater use of the calculator in 2016. In 1999, perhaps a greater use of other physical objects, manipulative materials, etc., to be able to help work out the calculation. And because we're relying a little bit more on the calculator, a little less on written objects, a little bit more on mental, then we use physical objects not as much. But certainly my plea will be for you in your classroom to always have manipulative concrete aids out for the students so that those kids who do need to use them have the ability to use those physical objects or those concrete aids. And in terms of numeracy, you might look at all those percentages and see that they don't actually add up to 100% or they add up to more than 100%. Why was that? Well, because we've used a rounding process. And guess what? That's okay. So even if we have a look at 86% in 2016, we have a look at 86% used a mental strategy, and we round off 14.6 to other physical objects, that in itself is 100%. But we accept because of more than one objects were used in more than one methods were used in calculations. So some used mental calculation and also used physical objects. We can accept that in this case, the sum is greater than 100%. Normally, we can't get more than 100%, but in this case, our numeracy tells us, and the knowledge that more than one method was used allows us to accept that purely as a numeric understanding, if not as a mathematical concept. And again, this is in Rees, your book, and the comparison between 1875, when there was only the two sorts of computations being done in schools, you can imagine very rote style of learning. 100 years later in 1975, pretty much the same, but we're allowing kids to estimate. Move on to 2015, that's 40 years later, and we're starting to use the idea of having a calculator. Mental computation has dropped because we're using calculator to support that, and we're increasing our understanding of the ability to use estimation. And then coming on to modern times, not quite today, but the future, it's looking at like that'll be divided pretty much equally, 1/3 estimation, 1/3 mental computation, 1/3 written computation, because we'll always have calculators available across any of those three things. But you can see where now we're prepared to accept things more as an estimate in mathematics. We don't need the exact final solution. Being numeric tells us that we can estimate, and we know that when we calculate something, our estimation complies with that, so that we know that we're in the right ballpark. But interesting to see the changes over that period of time. Now, mental computation needs to be considered as the first choice. Why? Pretty simple. It's efficient and it's importable because it's mental. It sits in your brain. And yes, you might need a pencil and paper at times for some jottings, but basically, wherever you go, your brain goes. So that should always be your first choice. One of the key understandings that we need to really think about is when we're looking at mental computation, we're not talking about instant recall. We're just talking about automatic recall. And automatic recall, or automaticity, is around about 2 seconds. It's a platform for successful computation of numbers of 2 or more digits. So what I'm saying is, even if we're looking at our tables and we're going to say 6 times 7, we don't expect that to be an instant recall anymore. We could think 2 seconds, 6 times 7, 1, 2, 42, because the students might be using some different strategies, which I'll unpack with you later, in order to arrive at that final solution, that final answer. And basic fact recall, the second dot point, is promoted through the use of thinking strategies. So again, we're moving away from rote learning. There's some rote that needs to take place, I guess, some remembering, but we try to underpin that with really strong understanding and providing concrete tools to support that understanding. But for you, automatic recall, a 2-second response is fine. We don't need kids to instantly recall things anymore. What do we need them to do? Well, in terms of their mental computation, we'd like them to know their basic facts up to 10 plus 10. We can look at that in a table. Excuse me. And also 10 times 10 in their multiplication tables. So the first steps in mathematics, which you'll hear lots about, mental strategies, just use basic facts, this word called partitioning. And you remember last week I said the language of mathematics can be quite explicit. Partitioning is another term we'll look at later. Place value is another term you need to come to understand if you're not sure what it means. And not just the word place value, but the interpretation of what the different places and their values are in our number system. So we need mental strategies to mentally work out an answer, and mental calculations refer to doing calculations in your head and involve much more than just a recall of basic facts. So it's also a processing of strategies in your head, which is the mental calculation of it all. And I'm just going to put a pitch in here, of course. I do believe when we're looking at our facts up to 10 plus 10, not just looking at our addition facts, but we should also involve our subtraction facts as well. Makes it easy for the kids. And if they're possible, when we're looking at our multiplication tables, we should also introduce the complementary division responses as well. But anyway, we'll unpack that a little bit more over the weeks. West Australian/Australian curriculum is divided into the 3 strands, which is the stem of the umbrella, if you can remember in the West Australian curriculum table I showed you earlier. So the 3 strands are number and algebra, measurement and geometry, statistics and probability, and hopefully those 3 terms or those 3 labels mean something to you, and we'll be unpacking those. Certainly number and algebra, number and algebra, then in Your maths 2 and 3, we're looking at measurement, geometry, statistics, and probability. But overarching all of those, and the idea of the umbrella, is this sense of proficiencies. And in the Australian curriculum, West Australian curriculum, the 4 proficiencies of understanding, problem solving, reasoning, and fluency sit across all of those 3 strands. And they don't really come in a particular order, although we could sort of surmise that perhaps we build an understanding with the students first. Then we want them to be fluent with their responses. Then we want them to be able to use that fluency and that understanding to help them solve problems. And then we want them to be able to reason about the solution to the problem that they've solved. We can't reason unless we've given the students the language with which to reason. So part of the understanding is not just teaching the mathematical concepts and strategies, but it's also carefully teaching the mathematical language. It might be words, it might be numbers, it might be symbols, it might be pictorial representations, or it might be things like graphs as well. But that's the West Australian curriculum, and we'll be unpacking that fairly slowly with you. So what is fluency? Directly from the curriculum itself. So students develop skills in choosing appropriate procedures. So they choose appropriate procedures. What's the understanding is, if you choose something, then you have to have a menu from which to choose. So we choose, when we teach multiple different procedures. We carry out those procedures flexibly, not in a fixed way anymore. We allow students to be able to think flexibly around the procedures. And then we do want this idea of accuracy to come into it, but more importantly, we want it to be efficient as well. And early attempts from students to work through strategies might be inefficient, but we accept that because they can work flexibly. But eventually we want them to be efficient in what they do, and we can guide them towards that without giving them one standard approach. And of course, we want them to choose appropriate procedures for whatever they're doing. In all of that, they need to recall factual knowledge and concepts readily. So they need to have some knowledge and understanding in their memory, and they need to have some working memory ready to do that. So the second paragraph talks about when students are fluent, what do? They calculate efficiently. They recognize robust ways, and I love the choice of that word robust because it means they recognize really strong and purposeful ways of answering questions. When they choose appropriate methods, again, the idea of choice means we have to give a menu of different methods, and we allow them to approximate or estimate, as we've spoken before. And when they do this, they can recall definitions regularly. They use facts and recall them. And when they can manipulate expressions and equations to find solutions. So again, you might want to just stop the slide and just read that for yourself and really take time to understand what it means. But fluency is a really important proficiency in developing of mathematical understanding, and particularly as it relates to mental computation as well. So here it is. Again, it's on the left-hand side. I've just put into a little bit of a dot point for you. So what choices do adults make in everyday life? What can you see there? Do adults choose appropriate procedures to suit themselves? I'd say yes. Do adults typically look at carrying out things flexibly? Yes. Can you recall your own factual knowledge readily? I'd say yes, to a point. Some might have a little bit more trouble than others. And are you being fluent as an adult when you calculate efficiently? You recognize robust ways of answering questions, not just different ways, different appropriate methods, recall and manipulate. So again, what we're trying to build in fluency in our student body is what adults need to use in their own life. And basically, that's what we're doing when we're being numerate as well. So what are some strategies to fluency? And we're going to unpack these one at a time. So the strategies we're going to be looking at, particularly in terms of the early mental computational work, is strategies called counting on and back. We're going to look at commutativity in addition, because there's also commutativity in multiplication. Hard for me to say. We're going to understand place value. We're going to look at related facts. We're going to talk about this thing called bridging tens. We're going to talk about doubles and near doubles. And then we're going to talk about the inverse relationships between subtraction and addition. But let's unpack each of those as we go. So the first one is counting on and back. And we need to move students from just counting on. So when we have little kids and we've got some beads out there, we get the kids to start at 1, move the bead over to, it's called a one-to-one correspondence. There's 5 counting principles, which we'll go through a bit later. But basically, it's not just always about counting on. It's not always about moving forward. We need to find lots of different ways that we can get the kids not just to count on, but also to count back, to look at their skip counting, if you like. So we can skip count by 2s. We can look at things like place values. We can partition numbers. So we can look at 5 is a combination of 2 and 3. We can show that using concrete materials. So counting on is really a good strategy to start off students' familiarity with the number and the number system, and the fact that each time we add one more bead to a group, that increases the number and the quantity in that's represented by that number by 1. So say there's 5 basic counting principles we need to cover. But once we've got that, let's move on quickly into some other strategies, because as the little graphic shows there, we only have so many fingers and toes which can help us to count on with. So let's look at this. 28 plus 37, of course it's a little bit more difficult than a single digit one, but that's deliberate. So we could simply count on 37 from 28. And we know we can use our fingers to do it. It's going to be pretty hard. We've got to phone a friend to come in because we'll need up to 40 fingers and toes for this. But we could count on 28 and we start 29, 30, 31, 32, 33, 34, etc. And we've used up all our 10 fingers and we've used up all our 10 toes. We've used up our friends' 10 fingers and we've used up 7 of their toes. And we've come to something like, 65 all up. So counting on's not particularly efficient in that place. So what else can we do? Oops. We can look at commutativity. And what's that mean? So instead of counting on, in the previous example, 37 from 28, we introduced a concept called think big, count small. And one of the ways we could count on would be start at 37 and count on the 28, be a little bit more friendly. But why can we do that? Because we have this property, the commutative property of addition, or the CPA, which says when we've got 2 numbers that we're adding together, it doesn't actually matter which order those numbers are added in. So A plus B is the same as B plus A. And the example down the bottom is if I've got 4 black counters and 3 white counters, 4 black counters plus 3 white counters, when I combine them into numbers of counters, is exactly the same as 3 white counters plus 4 black counters. So the commutative property of addition helps us rearrange the additions into more friendly terms. So again, 28 plus 37, if we were simply counting on, we think big, count small. We use the commutative property of addition to say, no, I'm going to start with my 37, then I'm going to add the 28, if I can find another friend to help. So commutativity is a really important property. And just think the commutative property of addition, I did say earlier there's a commutative property of multiplication, but does not work in reverse. There is no commutative property of subtraction and there's no commutative property of division. And we'll unpack that again as we progress through the course. So here's the example. 4 circles plus 3 circles equals 7. Really important, I'm going to make the point in a minute, that we don't always have the problem on the left-hand side and a solution on the right-hand side. Let's mix it up. So sometimes let's get the children understanding that we can start with the total, the equal sign, which I'm going to talk about, and then we can use our commutative property to say that 7 equals 3 black circles plus 4 black circles. So we need to change it up. And again, there's the example from earlier, 28 plus 37 or 37 plus 28. Think big, count small. Which one's easier to work with? What's the strategies that we're going to use to be able to separate those out? And again, we're still in this mental space. We can use some jottings, but we're still trying to calculate these mentally. Place value and using unrelated facts. Well, here's 3 strategies around 28 plus 37, or in fact, 37 plus 28. We can split along the place value line. So we can split the 28 into 20 plus 8, and then we've got the 37. Or we can split the 37 into 30 plus 7, and then we've got 28 plus 30. And you might be able to see that it could be easier for us to add the 8 to 37, which gives us 45, and then add the 20, which gives us 65. Or in fact, it might be easier on the other side, 28 plus 30, we know that 28 plus 30 is 58, and then we can, if we need to, count on 7 to get to the 75. So one strategy is, along the place value lines, is to simply partition one or two of the numbers. Second strategy is to split both. So we're saying 28 is 20 plus 8. We're saying 37 is 30 plus 7. And we can use our commutative property of addition to say that we can add those numbers in any order. So we can combine our 20 and our 30. We can combine our 8 and our 7. And that gives us 50 plus 15, 65. And the third strategy that we can use is what we might call an adjust and compensate. And we can use this sense of nears. So we know that 28 is nearly 30. There's 2 more to get to 30. So if we were to add 30 to 37, that's computation's pretty simple in our head. That's 67. However, we gave the 28 an extra 2, so we still need to take away an extra 2 to come back to the 65. So again, 3 strategies. Initially, 28 plus 37 looked fairly daunting, but if we use one of those 3 different strategies, the one that you understand, in fact, the one the student understands better, we can be quite efficient in our mental calculation. So let's keep going. So how do you actually add 8 and 7? What have you done there? Do you partition that? Do you use near doubles? Say 7 is nearly 8, double 8 is 16. I can take one away to 15. Do you partition them in different ways? How do you actually add 8 and 7? How do you actually add 20 and 30? Do you look at the zeros on the end and understand that's a name? So that's 2 10s and 3 10s, and means plus, so 2 10s and 3 10s is 5 10s, and 10s, the word actually has a symbol 0, so that gives us 50. Did you break 30 into 20 plus 10 and then used your doubles? 20 plus 20 is 40 plus 10. Lots of different methodologies, and perhaps even pause the lecture now and see if you can write down a number of different ways using those 3 strategies previously to partition or to break down the 20 plus 30. Okay, now let's have a look at these strategies. So here's a task for you. I want you to add all the numbers from 1 to 9 together. So 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. You might want to stop the lecture just while you do this. You might want a piece of paper to do some jottings. And when you're ready, start the video up and let's have a talk. Okay, so what strategy did you use? Did you add 1 to 2 to get 3? And then did you add 3 to get 6? And then did you add 4 to get 10? Did you add 5 to get 15? Add 6 to get 21? Add 7 to get 28? Add 8 to get 36? Add 9 to get to 45? Was that one way you did it? Or did you think about rearranging those numbers, for example, and make them a little bit friendly? So if I added the 1 and 9, that made 10. If I add the 2 and 8, that makes 10, so that's 2 10s. If I add the 3 and 7, there's another 10, that's 3 10s. If I add the 4 and 6, there's another 10, so I've got 4 10s, and we know that 4 10s are 40 with the 5 left over, so that's 45. Did you do it that way, or did you have another strategy to add all those numbers together? Lots of different pathways to achieve the same solution. All roads lead to Rome, just the path we take is slightly different. Okay, let's move on to this strategy called bridging tens and see what this entails. Okay, so to make 10, 10 serves as an anchor point, and we need lots of opportunities and lots of concrete materials and lots of different ways of looking at this to build the students' really robust understanding. Remember, I love that word robust, of lots of different ways to build a 10. So in the middle, if we're looking at this idea of adding 8 plus 7, if we've got the really strong understanding that 8 and 2 more makes 10, then I have this also simultaneous understanding that 7 is comprised of a 2 and a 5. So I can use my commutative property to say that 8 plus 2 is 10 plus 5 is 15. So we can break that down. Now, equally, another way of looking at it is we might think that, 7, I need 3 more to get to 10. 8 is 5 plus 3. 3 plus 7 is 10 plus 5 is 15. So lots of different ways of getting to that same answer. But again, we must give the students lots and lots and lots of opportunities, concrete opportunities to build this understanding. We're not going to do this by simply, as I'm doing to you, lecturing to you. With students, we need to build up that concrete understanding. And then we also need to know that this associative property of addition tells us we can add things in any order. So 1 plus 2 plus 3 is exactly the same as 1 plus 3 plus 2, or 2 plus 3 plus 1, or etc., etc., etc. So we have these two different properties of addition. In fact, multiplication is the same for these, that we can add a series of numbers all added together in any order. Our next strategy is doubles and near doubles, and you might have heard me refer to that in an earlier slide. So doubles and near doubles, we again teach the students to become familiar with these concepts through multiple opportunities of concrete manipulation of concrete aids. So when we've got things such as 4 plus 4 equals 8 and 5 plus 5 equals 10, we know that we call them doubles, and we can adjust and compensate. So if we've got, we know that 4 plus 4 equals 8, 4 plus 5 equals 9, and 4 plus 3 equals 7, because we can say that in this first example, 4 plus 5, well, 5 is 4 plus 1, double 4 is 8 plus 1 is 9. 4 plus 3 equals 7. Similarly, we know that double 3 is 6, and we know that 4 is 3 plus 1, or 1 plus 3, associative property of addition. So again, we can break that out. We're using an adjust or compensate strategy to create these doubles, near doubles, and then use that knowledge to help us understand and do the calculation. And we'll talk about this in shoots, but we need to really understand what a number string is and how this can actually work for students' understanding. Really important, nice little mathematical tool. Okay, this is an opportunity for me to get on my soapbox, because I think it's time that we really unpack this idea of the equal sign. And if we have this in the first example, was on the previous slide, 4 plus 4 equals 8, we tend to develop a conceptual understanding of students that on the left-hand side there's some sort of equation to calculation, there's an equal sign, and then on the right-hand side there's the answer. If we develop this pattern of thinking that an equation can only be represented like that, we create lots of fixed thinking in the students, and we don't want that. My preference is we talk to the students about that sign not being equal to, but equivalent to. And we also can say, then start to build understanding, and again, there's lots of tools to show this, that 4 plus 4 is equivalent to 5 plus 3. 6 plus 2 is equivalent to 2 plus 4 plus 4. We want to be able to break down and get the kids to be able to explore their knowledge and understanding. We don't want this fixed idea of an equal sign. We don't want this fixed idea of a problem, an equal sign, and a solution. We want to change that up. So sometimes we'll have the solution on the right-hand side is equivalent to, and then the calculation on the left-hand side, or we'll have two separate different calculations separated by the equivalent to. Really important to get this understanding. I always liken it to a balance beam, but anyway, I hope you get what I mean. And our last strategy is using subtraction and addition as inverse operations to each other, and how one builds on the other. So we've got this idea of change equations, if you like. This is where the problem is unknown. So 8 plus something equals 10. And again, we don't develop this through simple paper tests. We use lots of concrete materials, but we do it with the understanding that we can use this idea of equivalence. 8 plus something equals 10. Well, I can show using concrete materials that if I take 8 away from 10, that's going to be the same thing as the question mark, and we know in that case that the answer is 2. So we can manipulate our strategy to be able to produce a solution. So when the unknown problem, we can change, and we know that subtraction is the inverse of addition and vice versa. Again, lots of concrete opportunities for the students to understand that. Unknown problem, 73 plus something equals 100. Well, exactly the same way, if we can use this idea of equivalence, then 100 take away 73 is equivalent to whatever the question mark is in there. And if we do our maths, we know that's 27. We can play with that. If the unknown problem's at the beginning, something plus 2 equals 10, well, the same process. We're using the inverse relationships. We know that if we take 10 away from 2, it's going to give us that solution. So 8 plus 2 equals 10, 10 take 2 equals 8. Again, can't underscore it enough, we don't just do this with pencil and paper. We make sure the kids have lots of robust ways of using manipulative materials, concrete materials, to develop this understanding. And in the same sort of way, if we don't know what it is, something plus 27 equals 100, then 100 take 27, we're using the inverse of it all, and we can show that on a number line as well to understand that the answer is 73. So they're the strategies that we've used to develop mental computation skills. Easy to teach, but we need to actually make sure the students understand robustly when they're going to use them and the choice and the appropriate time to use which strategy. So strategies counting on and back, the commutativity, place value, related facts, bridging tens, doubles and near doubles, and then the inverse relationships of these. And I think that's about enough for this week. Thanks for persevering. I hope I haven't confused you at all. If I have, make sure that you talk to your tutor during the week. And have a great week. Bye.